Good morning, ladies and gentlemen, here to the group exhibit Hydrogen Fuel Cells and Batteries here in the Technical Forum. We will have all day very interesting presentations about this technology of hydrogen fuel cells and batteries. And if you talk about new technology, we also need some training and some research on it. And therefore, I'm very happy to have this morning here with me the Head of Research and Development of Heliocentris Academia GmbH, Dr. Stephan Funk. Welcome, Dr. Funk. And he will talk about new innovative training and research system, hybrid energy lab system. So enjoy. Please go
Thanks
ahead.
a lot, and thanks for having me. So, I want to talk today about our hybrid energy lab system, which is designed for advanced training and for research, applied research applications. So first of all, I would like to start with our hardware. This is a system consisting in a 19-inch rack with a fuel cell generator of 1.2 kilowatts. We have a battery for the hybridization and all the rest that you need to run the system. So within the rack there's a system control PC, there's an electronic load to load the system, and of course power distribution, sensors, converters. There's also an AC inverter for with a transfer relay for UPS applications. And the hydrogen to power our fuel cell is stored in metal hydride cylinders. So, very decent piece of hardware. We invite you to have a direct look of an operational system at our booth at C73. And but my talk today will focus a bit on rather the application side. And of course the usage in academia. So if we want to reduce the system or simplify it very much, we can say it's just a generator battery hybrid. That means there's a source, there's a tank, and there's a load. Yeah. So the source is of course our fuel cell generator. The battery with its filling level is our tank, and the load as a drain. So this is a simple but yet versatile model system for hybrid systems. You can study a multitude of use cases with it, because the complexity comes in when you see the temporal profile of the sources varying or of the loads varying. We all know that from the renewable energies we need storage. Of course there's a whole variety of use case scenarios and also their respective energy management. And our system is really designed to especially facilitate training in this area. Another complexity comes in when we look at the electrochemical nature of the components. Obviously, fuel cells and batteries are not that easy, and we need to train also on these fundamental effects there. So, and this is now our didactic approach for doing this in advanced training and in applied research. This might not fit for all cases of education, but for the advanced training and applied research, we think it's very suitable. So, it's always the three steps that we see here. It's observation and measurement, building a model out of it, and then applying what we can model in a fashion for controllers or for predictions. And in the observation step, of course, the sensors and the for electrical and physical observables are the key. But you also want to do the data acquisition and the visualization of the data that you take. In the second step of the modeling, then we use empirical models, for instance, to describe the batteries and the fuel cells. And this is needed because it is not that easy. Simply by measuring the voltage of a battery, you cannot determine the state of charge, for instance. You need to have additional information. And this is given by the models. To facilitate this, we think it's necessary to also do a curve fitting. That means we take directly the measured data and model and take can derive the model parameters with the tooling there. Yeah, of course, these empirical models can also be linked then to fundamental effects. That's especially interesting for electrochemical seminars or whatever. Yeah, this could be kinetics or the reaction kinetics or transport effects, which of course go into the equations. Yeah, in the application, I just mentioned the SOC calculation. That could be one application. Operating points on characteristic curves, also for visualization. Simulation is, of course, if you have a model, if you have the parameter set, you can simulate a system. And then, of course, all of this can be taken as an input for control applications or for control algorithms. And the idea is to really seamlessly integrate these three steps so that we can focus on the content and on the concepts and on the applications rather than on switching tools all the time. Yep.
Can you let us know what SOC calculation is?
Oh, SOC is the state of charge of the battery. So let's start with observe and measure, the first step of these three steps. This is a PID type of sensor overview, which is very commonly used in systems. So you have you know how everything is connected, how energy or material will flow, and you have all your sensors applied, and you can read them. Yeah, that is, of course, very handy to, at one glance, to see what's going on in the system. However, for advanced visualizations, it might be helpful to have real-time charts for, let's say, operating points here on the right side, where we can see the DC-DC converter with its input on the bottom and the output on the top, and we see the real-time working point. But we also see the lines, the limits, how it is configured. And of course, the DC-DC converter can be configured freely, so it's good to see where am I with respect to my limits. On the left side, of course, there's an energy flow diagram in a Sankey form. Also very good to see at one glance how your system currently is configured and where the energies are flowing. Yeah, in this particular example, we see a fuel cell coming from the bottom, starting with the energy content of the hydrogen. Then the fuel cell, which transfers it into heat and electric power. Then we see the DC bus in the red, and in this case the load, which is supported, and the battery charging, which is supported. Okay, now let's go. This was the part with measuring and data acquisition. Now let's talk about modeling. And for that, I take the example of the battery model that we apply. The idea here is always on the left side, we have a measurement, for instance, the discharge of a battery, fully charged, discharged over time. And with such a measurement, we can, of course, see certain things. And we try to derive a mathematical model out of this behavior. Obviously, if the observation is that there's a proportionality between the voltage and the current of a battery, we know there is an ohmic part. Of course, in the model of the battery, there has to be some ohmic part. Yeah, and the proportional constant is obviously the resistance. But there are other observations, like, of course, the capacity will expire. That leads to another term in the equation, which is a pole usually. Then we might have voltage peaks if the battery is fully charged. There's an empirical and exponential term to include that. And there might be some delay if you change the load conditions of the battery. There's a delay in how the voltage or how the battery reacts due to the electrochemistry going on, and this is modeled by low-pass filtered components. So the equations are written here. I don't want to go too much into that detail, but just to give you an idea how observation will drive a mathematical representation, which is the model. Okay, the model is implemented in our system in such a way that you can interactively play with it, first of all. Yeah. So the model equations are there, and you can select certain scenarios, charging, discharging, and by varying the parameters here on the left side, you can immediately see how the result will react. By that, you can really interactively approach these parameters and what effect they have on the model or on the outcome. So this is more to learn about the equations, how they work. Of course, if we have data, the more appropriate way is to do a data fitting. And for that, we implemented a module where you can load in, you load your data acquisition or your acquired data. And then by starting with a start parameter set, you can manually try to bring the model and the data into so that they give the same representation. Yeah. So you can do the fit completely manual by just varying the parameters, but you can of course do it also automatically with a Levenberg-Marquardt algorithm, which is a nonlinear damped least square fit, and then it will automatically give you the best result. So here in the chart on the right, we see a scenario where the battery is charged and discharged in about 2-minute circles. The blue line, the bubbles are the measured voltages, and the blue line is actually the fit result. So with this model, you can find quite good representations of your data. Yeah. The black curve, by the way, is the start parameter. So if you do a manual fitting, you just try to fit the black curve to the data. So this here is just to demonstrate how the battery model is validated for different use scenarios of the battery. So we have a scenario again with fast charging, discharging. We have a current ramp on the top right. We have a discharge on the top left, on the bottom left, and on the bottom right we see a charge scenario. And all of this data is fitted with one parameter set only. So obviously there are some deviations. Yeah, by that you can actually find out where the limitations of the model is. It's a simple model in the end. But what you can also see is that all the features are basically represented quite good. So we have a similar approach also for the fuel cell. So there's also a fuel cell model. I don't want to go into that too much. The equations are written here. Same module with start parameters and automatic fit possibilities. In this case, the fit is not done over time. So the x-axis is not the time, but the current, and the y-axis is the voltage of the fuel cell. So a typical characteristic curve. It's an industrial fuel cell, so at the end we don't see the real drop, because of course we don't go over the maximum power point in an industrial system. Okay, this is about modeling. And now the question is, of course, how can we apply this to energy management systems? And one application, as I mentioned before, is to visualize the operating points on the specific characteristic curves of the models. Yeah. So we can see this here on the left side. We can see it for the battery. In fact, it's a chart where on the x-axis we have the state of charge of the battery, and on the y-axis the voltage. And of course there are two branches. One is the charge and one is the discharge branch. In blue and in red, and the operating point. So the lines are always the model, and the points are the operating point. Yeah, a very good visualization to see where exactly we are in our with our battery. And if we don't hit the curve, we know we have a deviation. Okay, on the right side, the same for the fuel cell. On the top, the characteristic curve and the characteristic power curve, where you can see the maximum power point. And on the bottom, actually calculated efficiencies. So the working point of the fuel cell generator also with respect to its efficiency chart. In that case, it's the fuel cell stack efficiency only. Okay, there's also a simulated genset in here. I will come to that later. So that's one way of application. Another way of application is, of course, the advanced use cases that we want to do. Yeah, and for that also the information about the components is very helpful. So use cases could be, of course, again going back to this simple yet versatile model system. We have the source boost, where actually the battery boosts the source to provide higher powers, or to support load peaks. Of course, there could be range extender applications, charge management are very frequent applications in industry, uninterruptible power supply, obviously, yeah, and also genset efficiency solutions. If you're not familiar with that, that's actually when you cycle a battery in a hybridized system to avoid the partial load behavior of the generator. Partial load in a generator usually comes with low efficiencies, at least if it's diesel gensets. So, and then of course you want to study dimensioning. You want to study what type of power do I need to support my load. You have the temporal profiles as mentioned before. And you have to dimension your battery. Yeah, in mobile applications, this is very commonly known. How far can I drive with my electric car? These type of discussions. And of course, with all of this, there come control strategies for the energy management. And if you want to study those, then you want to simplify your system to these few parameters. And actually, what you see here on the right side is a direct screenshot from our control software, and you can see the symmetry between the DC-DC converter. In that sense, it's the control at the source, at the generator, and the electronic load. And then you also have the state of charge. So you can. There's a full symmetry in generator and load, and you can play with that and apply it to your own research. Control strategies could, of course, be you want to minimize the runtime of your generator, yeah. The cycling of battery as in a genset efficiency solution. Also, working point for the SoC you might want to control on. This could be for grid stabilization or so. Yeah, there are battery power supplies which do something like that. Yeah. You could also want to buy the current when it's cheap and sell it when it's expensive, and then you have a different control strategy. You might want to include weather prediction, load prediction, whatever. So, and to do this, these complex management scenarios, of course, they are not included in our system. Our system is the base to do it. But we provide an API, an application program interface, so that you can integrate the system into your own studies, into your own control mechanisms. So if you have a layered control topology, for instance, in an Internet of Things type of scenario, yeah. Advanced energy management algorithms you could also implement. Yeah, we have some. I'll come to that in a minute. Yeah, you could want to have more complex, including forecasts, for instance, then you can do it by yourself and use the system to execute whatever decisions you make. Alternative battery models, integration into databases or data acquisition setups. That's what the API is for. Okay. So I was told I have some time, so I continue with a special thing now with respect to hybrid energy management. We do have a hybrid energy management built in the system, which is a battery cycling algorithm with a load-dependent switch-off condition. So what we see when we come here from the left is that the state of charge, the orange line, goes down, and also the voltage of the battery goes down, and at some point we trigger the generator to switch on automatically, and you determine the threshold. And then the battery will be charged and the load will be supported. Yeah? So on the right side in the Sankey diagrams, we see in the charging phase that the battery and the load are supported by the fuel cell. And then, if the battery is fully charged, we switch off, and then the battery supports the load. Actually, the switch off is not only the SOC of the battery, but it also includes the load. So what we see here is for a constant load scenario. If the loads vary, you might want to let your generator run even though the battery is full. So there's a current threshold to switch off the system. Yeah, so this is a cycling algorithm, which is very useful. You can just leave the system running forever, more or less, if you configure it in a proper manner. So I want to make a small insert. There's a third model which we implemented into our software, which is the fuel consumption curve of a combustion engine. A very simple two-point model, where you can also see the black line is in fact the efficiency curve of the genset. On the x-axis we have the power of the genset, so the operating power, and we can see the partial load behavior here of the system. Yeah, so this is a very simple model. It's also scaled to our energy level then, of course. And then we can calculate how much fuel would we need if it was not a fuel cell, but if it was a genset. And then just one application is that we can in the cycle algorithm, so if one cycle is completed, we can determine whether we have efficiency gains or losses by cycling the generator. And that's actually the genset efficiency solution that is quite common in industry. Yeah. By completing a complete cycle, of course, we can also integrate the electronic work of the battery itself, and by that we can determine the also the efficiency of the battery itself. So, with that, I'm done. I want to thank you for your attention, and I would like to invite you to our booth at the C73, where you can see the operating system. And I will also be happy to explain details if you are interested.
Thank you very much, Dr. Funk. Here's your applause.
Thank you.
So are there any questions from your side? Just raise your hand. You can take your question right away, and Dr. Funk is happy to answer you.
Oh, yeah.
I have one little question to you, Dr. Funk, because in talks about new mirrors and new fuel cell applications, and so there's always the need to prove durability of these new fuel cells. And you're doing these fuel cell models and battery models and even genset models. Mm-hmm. Is it also good for simulation one day? Could you evolve it into a simulation tool?
Yeah, our system is really designed to integrate it rather in a in the overall control strategies of these things. So if you want to do really fundamental research on MEAs, on fuel cells and so on, there probably you want to use different models. Our models are rather empirical models, which are very good for simulating the usage. Yeah. So if you have a real life use case scenario, and you want to simulate that. Obviously, with our API, you can also include it in a hardware in the loop type of manner. You could include it into MATLAB Simulink or whatever you wish. Yeah? You could also take simulations from Homer and compare it to the measurements that we have here. Obviously, actually in MATLAB Simulink there's also you can implement anything in MATLAB Simulink, but there's also our battery model, for instance, they also use in
Okay.
or it's available for MATLAB
Okay,
simulating.
very good. Thank you very much. So if you have any further questions, just visit Dr. Funk here at C73. That is just down the aisle, just to the other end of the hall. So it's really rather big here, the group exhibit.
Yeah.
And you'll find you there and discuss further details with you. Once again, thank you very much, Dr. Funk, for being here. Thank you.
Thanks a lot. Bye.
I have to announce to you that the next presentation from Hydrogenics Corporation, Dennis Thomas was announced, won't happen here. Unfortunately, he won't speak about high response project, recently finalized emergency response training. Maybe he's on this training, I don't know. I'm sorry for that. But the next presentation here on stage is at 11 o'clock about porous metals, characteristics and advantages for use in alternative energy applications. This presentation will take place here at 11 o'clock. We are waiting Robert Saunders. He's Technical Sales Engineer, Applications Engineering of Mott Corporation from Connecticut in the United States. So just stay here for another 15 minutes, have a coffee on the house, and we will start at 11 then. Thank you very much.